AC motors. There are many types of AC motors. The most popular motor, and the one I will discuss, is the simple induction motor. You apply a voltage. As the current starts to flow through the windings, a magnetic field is created in the armature or stator. An easy way to remember the name stator is it's the part of the motor that stays still, stator. The magnetic field builds and has an effect on the rotor, the part that rotates, which is made of steel laminations pressed together. The effect is it starts the moving of the steel rotor. This movement also creates a magnetic pushback that affects the magnetic field being applied. All of this, with the combination of the AC phase changing 60 times a second, is what keeps the rotor turning. The constant pushing and pulling of opposing magnetic fields is also what creates the impedance in the windings of the motor and alters the frequency inside the motor. If the motor bearings seize up, or the work we are doing slows the shaft or the attached rotor too much, the magnetic reaction changes. The built-in impedance is changed, and we risk burning up the motor windings with high current. No matter what type of motor you are dealing with, whether it's induction or synchronous, shaded pole, capacitor start, or even DC, you have to have an alternating current to create a magnetic field that is needed to make the motor turn. Motors come in many different voltage ranges. Make sure you read the data tag and wire it up to the proper incoming voltage. Read the wiring instructions. Many motors, especially ones that will run off different supply voltages like 120 or 208, as shown in the picture, will require you to wire it up differently. Motor design can get very complicated in special applications, especially today with climate initiatives. Motors designed for energy savings is creating a lot of special application motors, from variable voltage to variable frequency. Don't be surprised. General testing for simple induction motors can be accomplished. The first thing is doing a winding test using your ohm scale. You cannot use Ohm's law. If you have a motor rated for 120 and we use the coil resistance, we will see an amperage much higher than rated. The opposing magnetic field is the resistance. You're just looking for continuity through the windings. You can get specific winding data from the manufacturer if you want to know the exact resistance you should read. You want to check to ground or the frame to ensure you have infinite ohms to ground. If you read any continuity to ground from a winding terminal, your coil is shorted. If you have split phases, which is a specific motor type, check each winding to ensure the windings aren't shorted to each other. Next is the running test. Check the incoming voltage to ensure it is correct. At the correct voltage, what is the amperage? Is it within 10% of the rated amperage while it's under load, doing the work it is supposed to do? If it's not, then you have to determine why. Is there another factor other than the motor itself causing high amps, like an improperly adjusted pulley, wrong fan blade, blocked air path, or bad bearings on the component it's turning? On the data tag, you will find much data. When you are replacing a motor, make sure the motor you are purchasing matches the data of the motor you are replacing. Things you want to consider are the size of the motor, the frame, will it fit where we need it to? The mounting, will it mount in the existing location? Then you get into voltages, amperages, duty cycle, and frequency. Remember, if you buy a dual voltage motor, the incoming terminals must be wired for the correct voltage. Then you get into temperature ratings. Does the motor run clockwise or counterclockwise? How does this particular manufacturer determine rotation? Is it a reversible motor? And what is the application? If you are in doubt, you should always consult the equipment manufacturer. Three-phase motors can run in the wrong direction if wired incorrectly. Don't worry, it's easy enough to change the direction. You just swap two incoming power lines until the motor runs in the correct direction. The phase shift determines the starting direction of the windings relationship to the rotor. In capacitor start motors, the capacitor is in the circuit boosting the incoming voltage until the motor reaches a specific speed. Once that speed is reached, a centrifugal switch inside the motor opens the start circuit. The start winding is no longer receiving power. This will be when your motor reaches its running rated amps. It usually happens so fast technicians miss it. In compressors using start capacitors, the start relay is controlled by amperage. It's important to understand that the capacitor in the circuit will temporarily give you a high voltage reading because of its ability to react higher than the applied voltage across the start winding until the switch or relay take them out of the circuit. Cap motors that just sit and hum until you spin them by hand and then they run great typically have a bad capacitor. Troubleshooting a motor will be much easier if you understand all the variables.